Namaskar my dear friends. Let us talk about Ethernet physical layer transceivers. So how Ethernet transceivers can be designed with a particular schematic design. So what we'll do is we'll try to understand schematic design concepts and at the same time lot of related terminologies related to Ethernet PHY. Okay. So the thing is you can understand very easily. We have, let us say this is the Ethernet PHY. So Ethernet PHY will be having all the layers like PCS layer, PMA layer and PMD layer. I'll tell you what are these layers and what is their definitions. However, to the left side it will be connected to the MAC, that is nothing but your, let's say, microprocessor or FPGA, and this will be connected through the transmission and receiver lines like TX 0, 1, 2, 3 like that and RX 0, 1, 2, 3 like that, and some of the control lines. And at the same time towards the right side you will see we will be having network, okay, and that is nothing but MDI, media dependent interface. Okay, so in that case what happens is these are connected to my differential transmission line and differential receiver line, that is RX plus and RX minus, or RD plus RD minus will be taken. As you can see this goes through some of the isolation or like like isolation and coupling transformers, and then it goes to the RJ45 connector. So this is my RJ45 connector. These days almost all the RJ45 connectors are coming in built transformers, so we don't have to have separate parts for transformer and then RJ45 connector, they will be inbuilt together. We have taken an example for this particular Ethernet PHY, which is DP83826, and this is capable of giving you 10 Mbps and 100 Mbps for industrial Ethernet PHY connections. It is also compliant to IEEE 802.3. However, our main understanding will be what is Ethernet and what are the different terminologies that is utilized. So as you can see, we have lot of places that Ethernets are used. You have seen either in your servers or computers, or like many of the places. However, you may be willing to design the particular circuit related to Ethernet connections, right? So in that case, as you can see, first of all, let us try to understand some of the features that we need to look into while selecting a Ethernet PHY. So I have taken one of the data sheet and from there I have collected the features. So these features can be very easily understood, like we should see transmission latency and receiver latency. Okay, like what is the latency time? It must be very less, which is like 40 nanosecond and 170 nanosecond. Then we should also see some of the system solutions, like it has enhanced EMC circuitry, integrated EMC circuitry. It is capable of IEC 61000-4-2 ESD, which is of 8 kilovolt contact and 15 kilovolt air. So that is very robust, a standard that is already there for EMI-EMC application. We have EFT, which is IEC 61000-4-4. So that is capable of up to plus minus 4 kV. It is having conducted emission and radiated emission with class B according to CISPA 22, and there are all other features also, like you can see it has a capability of 150 meters of cable reach, and it has a voltage tolerance of plus minus 10%, and at the same time it has enhanced mode for additional features and basic mode for common Ethernet pinouts, and it is having very low power consumption as well, which is less than 160 milliwatts. There are MAC interfaces that we will talk about. This is the main terminology that we'll be talking about right now. So this is having a capability of MII as well as RMII. Okay, and other things is we have to see what is the supply ranges, like it is capable of 3.3 volt power supply, only one is enough, and it has a IO capability of 1.8 volt and 3.3 volt. At the same time it is having a temperature range of minus 40 degree centigrade to 105 degree centigrade. There are all other temperature range available, which is 0 degree to 70 degree, then 0 to 85 degree, right? Then minus 40 degree to 85 degree centigrade, or like minus 40 degree to 125 degree centigrade. All these things are there. As high as it can go up to 150 degree centigrade also. Okay, and you can see it is compliant of IEEE 802.3 compliant for 10 base TE and 100 base TX. We have 1000 base TX also, so that will be 1 gigahertz speed. Some of the applications that you want to see for this particular Ethernet PHY transceivers is we have a utilization of this in factory automations, robotics, motion controls, and then we have motor drivers, grid infrastructure, building automations where you will be requiring lot of LAN connection so that it will be utilized. We have industrial Ethernet field buses. If you want to utilize in consumer electronics, you can utilize this in consumer electronics as well. There are a lot of game consoles these days which requires Ethernet PHY. And then we have printers which is connected to a LAN these days, so directly you can send your data to printers and it can print it very easily. Then we have HMI, IP cameras, so all these places this can be used. So let us try to understand how Ethernet PHY is actually again connected. So as I already mentioned in the beginning itself, this is the Ethernet PHY IC that is there in the middle, and that has integrated MAC terminations, and this will be connected to the MAC like FPGA or something like that, and this will be having master slave configuration or master configuration or slave configuration that we will be talking about later, but it has a capability of getting connected through MII and RMII. Then it has SMI also, like a station management interface, so that will be through MDC pin and MDIO pin. This is 2-wire pin which is nothing but management data clock and management data IOs. Okay. Then it has reference clock as well, so this is how it will be having interface through the MAC. Coming back to the magnetics and the network side, so this is called MDI, that is media dependent interface. So it is having integrated MDI terminations where directly you will be connecting it to the magnetics, that is transformer, 1:1 transformer, and then it will get connected to the RJ45. Okay, so this will send the data to the network. So this is how the overall picture is there. Now if we talk about some of the pins that will be required to do this interfacing, so just try to keep this in mind. Like we will be having Ethernet 5 pins as, let's say, VDDA pin, that is analog supply pin, then VDD IO pin. Okay, that what is the IO level, logic level, which can be 1.8 volt or 3.3 volt. Then we have differential transceivers line, that is differential receive line and differential transmit lines. Okay, so RD minus is negative and RD plus is positive. Similar to that, TD minus and TD plus is there. We have oscillator pins which will be acting as a XI and XO pins, and we have R bias pin. Okay, then as I already mentioned, we have MDIO pin and MDC pin. So these are actually used for management data IOs and management data clocks. Some other pins are there. As you can see, we have RxD lines, so that is going to be 4-bit lines. If you want, you can utilize lower bit numbers also, like only RxD0 and RxD1 will be enough for 10 Mbps. Okay, if you want to increase the data speed, that's the reason we are going to have higher number of bits. Then we have receive data valid lines, and then we have current carrier sense data valid line. Then we have receive clock line and receive error line. So all these indicators will be there for your Ethernet PHY to MAC interfacing. So these are receiver side. If you see transmitter side, same way this will be also interfacing between Ethernet PHY and MAC. Okay, so this is my Ethernet PHY, and this will be going to the MAC. So as you can see, we have transmit also 4 data lines are there. Then we have transmit enable, then we have transmit clock, and we have transmit error signals, and some other lines are there which is called as LEDs. So LEDs indication will be there, like LED 0, 1, 2, 3, all these will be there. Okay, and similar to that, other more lines are there which are also called as let us say we have some call lines, or something like that, like let's say call line is there which is called as like collision detect lines. Okay, and as I already told you, like CRS line which is carrier sense lines. Okay, we have reset lines also, it is also called as RST_N, so that is reset line. So with these informations you will be able to interface your Ethernet physical layer transceivers to the FPGAs, right? So let's, in a nutshell, we will try to understand what are the different terminologies. So as I have been talking to you MII, so MII is nothing but media independent interface. Okay, so that will be between MAC and Ethernet. Then RMII is also there, like you, if you have to reduce the data rate, then you can go ahead with reduced media independent interface. It will require less number of pins for interfacing. If you go ahead with gigabit in media independent interface, that is GMII. Then we have serial gigabit media independent interface. It will be requiring even less number of pins, that is SGMII. Then we have SMI. Just now I told you about MDC and MDIO lines. Okay, so that will be, this is called as MDC and MDIO line. Okay, so this will be a station management interface. Then we have inbuilt layers, which is called as MDI, that is media dependent interface. Then PCS, that is physical coding sublayers, and PMA, that is called as physical medium attachment layer, and we have PMD, that is physical medium dependent layer. So these are the terminologies that you must have in your mind before designing the Ethernet PHY schematics. If we talk about complete connection of Ethernet PHY with the MAC and the network, so as you can see in a very good nutshell, this was taken from Texas Instruments training, so they have made it very beautifully. So this is my Ethernet PHY IC, and we have transmitter and receiver data lines that is connected to the MAC, and we have some controls and a status signal and control signals, okay, through the MAC. So this is all called as MII, that is your media independent interface. And media independent interface has different categories like RMII, ZMII, RGMII, all these things just now I told you. It has a reference clock pin which will be taking from either oscillator or directly from the MAC also. It can take like FPGAs or something like that. That will be taking either 25 megahertz or 50 megahertz clock will be there directly. Okay. Coming back to the PHY to network connection, so we have MDI line, that is called as media dependent interface. This will be differential transmit lines and differential receive lines. So there will be AC coupling, that will be through the capacitors where isolation will not be required. And if you need isolation, then magnetics will be utilized, which will be 1:1 transformer that we will discuss just now. Okay. And as you can see, a very good versatile connector is there, which is RJ45 connector. These days RJ45 connector are coming up with inbuilt magnetics, so there is no need of extra separate magnetics, and then this will go to the network. There are a lot of LED indications, so instead of connecting the LED into the PHY transceivers, it can directly inbuilt into your RJ45. That's the reason you will see whenever you plug in your RJ45 connector network, you will see some of the blinking LEDs. So this is actually driven by these LED indicators. So why don't we proceed with some of the Ethernet port details, so that we can understand how many lines are required for different MII interfaces, right? So let us first talk about MII interface. So you can see Ethernet PHY port details in MII. This will be according to IEEE 802.3. So as you can see in MII, we need 4 bits of TXD lines for TMAC to PHY transmit data lines. So from PHY to MAC, this will be the transmit lines. We have TX enable, TX error, that is all TX means transmit, okay. And then similar to that we have RXD lines, that will be 4-bit RXD lines, and then we have RXD data valid, that is receive data valid lines, and then we have receive error lines and receive clock and transmit clock. So what is the thing that we have to understand? 4 bits will be there for transmit data lines and 4 bits will be there for receive data lines. Then we have transmit enable and we have transmit error. Similar to that we have receive data valid and then receive error, and there are 2 clocks which will be receive clock and transmit clock. So this is the overall Ethernet port details for your MII interface, okay. And MII interface will be supporting you either 10 Mbps or 100 Mbps, okay. So that's the reason it is called as 10 base TE, or it is also called as 100 base TX, okay. So this is how for 10 Mbps it is 10 base, for 100 Mbps it is 100 base, okay. Now let us talk about some other Ethernet port details. So we'll talk about GMII, that is also called as Gigabit Media Independent Interface. So in that Media Independent Interface, only changes that you will see is instead of 4 bits TXD lines, it has 8 bit TXD line. Okay, so from 0 to 7 it is 8 bit TXD line, and similar to that we have 8 bit RxD line as well. Okay. Then there is another signal which is called as GTXCLK. Okay, so gigabit transmit clock is there, which is extra, and other than that all other are according to your MII signal only, that is TX enable, TX error, then we have RX data valid, RX error, and similar to that we have RX clock and TX clock. So only change that is happening is we have additional GTX clock, that is your TMAC to PHY transmit clock, and we have 8 bits of transmit and like receive data lines for the MAC interface. Okay, and MAC interface is nothing but we are trying to always talk about FPGA because we have worked with a lot of FPGA design. So this is how we will be utilizing FPGA to Ethernet PHY transceivers. Okay. Coming back to the reduced ones, so we will talk about reduced GMII, that is reduced gigabit media independent interface port details. So as you can see in reduced, we have instead of 8 bits we have 4 bits. Okay, so 4 bits will be this and then 4 bits will be this. Rest other lines will be almost same, however it has very less number of connections, so that you can have the interface between MAC and Ethernet PHY with less number of lines. Okay. So we have transmit control lines, and then we have transmit clock, like transceiver clock, transmit clock is there. Then we have receive control line and receive clock is there. That's all. So receive control, receive clock, and then transmit control and transmit clock, and 4 bits of receive and transmit data lines for the MAC interface. Okay. Good. So with this, I think you have a pretty good idea about how Ethernet port details are there and what are the different terminologies. Let us quickly try to understand from the data sheet that we had seen. So this was all about media independent interface, that is MII, and just now I mentioned that this is called as data signal, which will be TXD lines, which is 4 bits, and RxD line, which is also 4 bits for MII signal. Okay. And similar to that we have transmit and receive signal, which will be your transmit and receive data valid. So transmit enable signal is there and receive data valid is there. Okay. Then we have some of the line status signal, which is called as CRS, that is nothing but carrier sense signal, and then we have call line, that is nothing but collision detection line. Okay. And we have some of the error signal, which is also called as RX error. So with these lines you will be able to have PHY and MAC interfacing. So this is all about MAC signaling. Okay. Now if you talk about RMII, let us say reduced MII, so in that instead of 4 bits it will become 2 bits. So as you can see we have RMII. So RMII is having 2 bits of receive data lines and 2 bits of transmit data lines, and then we have receive control, which is going to be TX enable, and transmit control signal, which is going to be carrier sense data valid. So this requires very less number of signal lines so that you can interface your Ethernet PHY to the MAC. So you can see Ethernet PHY to the MAC, it has been made the connection or interfacing. If you talk about RMII like master signaling, so that's not required right now. Let us move to the next, which is going to be typical application. So as you can see in typical application, this is my Ethernet PHY IC. Ethernet PHY IC. So Ethernet PHY IC will be requiring one analog supply voltage, which will be 3.3 volt right now, and it will be requiring one logic level voltage also, which is for IO voltage level. So that can be either 1.8 volt or 3.3 volt. Okay. Next, it will be requiring some of the LED status, so that will be directly either inbuilt into the RJ45 connector, or you can keep it separately on the board, right? Then it will be requiring clock sources, which can be supplied either by the crystal oscillator, or it can also be supplied from the MAC, which will be acting as a master, and this will be acting as a slave at that time. And this is the MAC and Ethernet PHY signaling, which is going to be either MII mode or RMII mode. Okay, that is your reduced media independent interface through the FPGA. And next comes to the network connection, so that is going to be through the magnetics, and then it is going to the RJ45 connector. Okay, so it has only two capabilities, which the IC which we are talking about is DP83826, and this is going to be connected like this. Okay, so if you want to see how magnetics are connected, so as we have already explained you also in our previous long videos, we'll like quickly do that here as well. So as you can see here, Ethernet PHY, you will be having transmit data lines which is in differential form, that will be TXD plus and TXD minus. Similar to that, receive data lines will be there in differential data lines, which will be RD plus and RD minus. Okay. So in that, after this particular transformer isolation, this is going to get connected to the RJ45 connection. Okay, and these days RJ45 connectors are coming in built filters, so this will be actually inside this, but I have connected it separately right now. There are something which is called as coupling, so this is 2 nanofarad coupling capacitor here, and here also 2 nanofarad coupling capacitors. So these are the two pins, which is nothing but, I'll just tell you, this is CTD line and CRD lines. Okay. Similar to that, we need some match resistors. So for that, like match termination is required, and that is called as 75 ohm match termination for the output side, and this is also 75 ohm output side. And then this will be going to the earth with 0.01 microfarad if you want, with minimum you keep 100 volt 1000 volt ratings. Okay, so this is how it is, complete connection is there. As you can see how my transformer schematics look like, so it will be looking like this. We have TD plus line, TD minus line, and the beauty these days is these transformer are made specifically for the network connection to the RJ45 connectors, and they are pretty good, like arranged in this fashion. So you can see lot of like pictures are there for transformer schematics. So you can see we have TD plus, TD minus, CTD line, then RD plus, RD minus, and CRD plus line. Okay. Then we have output side, it is going to be TX plus and TX minus, and similar to that RX plus, RX minus, and we have CTX and CRX, and this is going to get connected to the RJ45 connector. Okay, so these lines are coming from Ethernet PHY outputs, and this will be connected to the RJ45 connector so that the data can be sent to the network. And if you see quickly inbuilt RJ45 connector, so all these things will be inbuilt in a one connector, and this connector will be having green LEDs and yellow LEDs also inbuilt, and inside that only the termination resistors will be there, so you don't have to put separately. Okay, and these signals will be coming from your Ethernet PHY transceiver ICs, so that will be TD plus, TD minus, TCT, RD plus, RD minus, and RCT. Okay, so this is very simple connection with inbuilt filter in the RJ45 connectors. So alright guys, hope you have now a very good understanding of how to design the Ethernet PHY transceiver schematic design and what are the different terminologies that are involved. And if you do not need isolation, then you have one more option, that will be DC blocking capacitor. So you can avoid this particular transformer and put just capacitors from TD plus line to your TD RJ45 connector lines. Okay, so this differential lines, transmit lines and receive lines directly can be connected through the DC blocking capacitors where isolation is not required, and this is the way you can reduce lot of cost, and this is how you can implement it very easily. So alright, if you do have any queries or any question regarding the terminologies involved in the like Ethernet PHY terminologies and what are the different connections or different lines that is utilized, please put down your queries in the comment box and we shall be able to answer you out properly. Thank you so much.